Welcome to The Privacy Effort. I'm Frank. In the next few minutes, I want to take you inside one of the most revealing moments in cloud history, the massive AWS outage that hit U.S. East 1 on October 20th, 2025. This wasn't just a technical hiccup, it was a full-scale stress test of how fragile our cloud dependencies really are. In this talk, we'll explore what actually happened, how a simple DNS issue spiraled into a global paralysis, why recovery turned out to be harder than the failure itself, and most importantly, what it teaches us about the hidden risks baked into the modern internet. By the end, you'll walk away with 3 concrete strategies for protecting your own systems: how to rethink consistency, decouple from regional dependency, and practice failure before it happens. Let's dive in and see what this outage really exposed about the cloud we all rely on.
Today, we're opening the post-mortem report on that massive AWS outage, specifically the one at US East 1 on October 20th, 2025. It was quite the event, a day when a huge chunk of the cloud, everything from critical banking applications to your Alexa at home, simply fell silent. This wasn't just some server blip, it felt like it exposed a fundamental fragility in the modern internet. This deep dive really matters, because it exposed something big, the moment when all our comfortable assumptions about the cloud just cracked. And here's the twist you need to know right away. This wasn't your average outage. It wasn't just one server going dark, or a few zones glitching out. It was a regional control plane failure, the kind of hidden, behind-the-curtain collapse that hits right at the brain of AWS itself. And that's what makes it so unnerving, because if the control plane can go down, it means the high-availability blueprints we've all been told to trust might not be as bulletproof as we thought. My mission today is to unpack the story of this collapse. Why was the recovery so messy? How did a seemingly simple DNS issue escalate into a crippling global headache that dragged on for over 12 hours? The timeline itself is fascinating. The disruption kicked off just before midnight Pacific time on October 19th. Within that first hour, AWS was already acknowledging major issues brewing in US East 1, the massive Northern Virginia region. The blast radius was immediate and terrifying. We saw huge problems across the board. Critical financial apps like Venmo stopped working, major gaming platforms such as Roblox and Fortnite stalled out, and even government services like the UK's HMRC, along with essential sites like Amazon.com, were impacted. But the scope isn't the whole story. The real narrative, the part that truly gets interesting, is how long it took to fix. The initial technical fault was identified as a DNS resolution issue tied to the DynamoDB API endpoint, which is foundational. DNS, often called the Internet's phone book, is critical. AWS supposedly identified and mitigated this issue by around 2:24 a.m. Pacific time. You'd think the problem would resolve relatively quickly after fixing the root cause. But no, the crisis was actually just entering its most destructive phase after time's the fix. How does that happen? Because the attempt to recover triggered massive secondary impairments. Internal systems, such as the EC2 instance launch system and network load balancer health checks, began failing due to the recovery effort. This state of operational paralysis is precisely why the problems dragged on until 3:01 p.m. Pacific time, over 12 hours after the initial DNS issue was supposedly fixed. This brings us to the big question. If we as customers pay for redundancy and are constantly told to build across multiple availability zones, why didn't the cloud simply fail over? Why didn't it recover smoothly? Why was the recovery itself the next disaster? That's the million-dollar question. And to understand it, we have to look at the psychology behind it all. This fragile foundation. Why is everyone so reliant on US East 1 in the first place? It really comes down to the concept of monoculture. Cloud services promise incredible reliability, but building true redundancy across different cloud platforms, a genuine multi-cloud strategy, is architecturally complex and, frankly, expensive for most businesses. So they pick one provider, usually AWS or Azure, and stick with it. If you choose AWS, you almost inevitably become deeply tied to US East 1. Why? Because it's the oldest and the biggest. But here's the hidden vulnerability. the part that truly matters. US East 1 acts as the home of the common control plane for many critical global AWS services. For someone running an application, this means that things like IAM, the Identity Service Updates, or DynamoDB Global Tables often have their primary control functions running out of US East 1. So even if your app is global, its brain might live in Virginia. That's a good way to put it, and it's the core distinction you need to grasp. You might deploy your application across multiple availability zones, multiple data centers within US East 1 for high availability. This protects you if one building has a power outage. However, that multi-AZ setup offers precisely zero protection against a failure in that central regional control plane. If the shared identity service or some other core regional service goes down, your application, no matter how well you spread it across AZs in that region, is simply stuck, waiting for the regional brain to start working again. It's a single point of failure, just at a higher level than we usually consider. There was also analysis looking at the human factor, specifically the time it took to even figure out the initial problem. Analysts definitely pointed out that it took 75 minutes just to identify the initial DNS root cause, which seems alarmingly slow for a company of AWS's scale and expertise. This raises questions about the organization itself, the team tasked with fixing it. It brings up the brain drain argument. When you see slow responses to these really specific, complex, deep failure modes, it can suggest a loss of institutional knowledge. Perhaps the tribal knowledge about how these intricate systems fail isn't as strong as it used to be, meaning the engineers who built it or knew its quirks might have moved on. When that deep expertise leaves, the teams left behind might be facing genuinely novel problems under immense pressure. Some analysts saw this as possible evidence of the organization hollowing out its engineering ranks. That's a sobering thought, the system's complexity potentially outpacing the knowledge needed to fix it quickly. It's certainly a risk in any large, complex system. So that sets the stage. Now let's dive into what actually happened. The mechanics of the collapse. The technical script broke down into three parts. First, the initial domino was a simple DNS issue, as simple as these things get anyway. A DNS resolution problem essentially prevented client applications and SDKs from looking up the correct address for the DynamoDB API endpoint, specifically in US East 1. So the phonebook entry for DynamoDB in that region essentially vanished. Next came the amplification, and this is key. DynamoDB isn't just some minor service. It's used for almost everything internally at AWS and by customers. Login sessions, rate limiting, feature flags, configuration, foundational stuff. So when applications all over the world suddenly couldn't resolve that name, their software, the AWS SDKs, did exactly what they're programmed to do in case of failure. They back off briefly, then retry aggressively, perhaps with some jitter in the request timing, and then hammer the network again in these exponential ways. Try, try, try again. So the built-in recovery mechanism, trying to reconnect, actually turned the failure of one service into a massive stampede of requests. It effectively created a self-inflicted denial of service attack on AWS's own internal network. The cure became the disease, a huge internal traffic jam, all caused by everyone trying desperately to reach that unavailable DynamoDB endpoint at the same time. That explains the amplification. What about the long tail? Why did it take so long to clear up after DNS was fixed? Even once they fixed the DNS lookup problem around 2:24 a.m., the internal systems were completely flooded, overwhelmed by this enormous backlog of retries and queued requests generated during the amplification phase. They were still dealing with the traffic jam. So, AWS had no choice but to throttle operations to prevent a total meltdown. That meant things like launching new EC2 instances became really slow or failed. SQS message queues stalled. And Lambda function invocations were limited. Even though the original problem was gone, the system was still choked. Services like AWS Config or Redshift reported having a massive backlog of messages to process, which took hours to clear. That's why users still felt degraded service well into the afternoon, long after the root cause was fixed. That paints a pretty clear and frankly scary picture of how things cascaded. We've seen the catastrophe. What can we actually do about it? We need a resiliency blueprint because we can't stop AWS from having outages. While you can't prevent them entirely, perhaps we can change our own architecture so we don't pay such a high price when they happen. This is where we get practical. Let's focus on 3 concrete rules for managing this specific risk, the dependency on US East 1. Rule 1. Rethink consistency. Seriously. When modeling your application's dependencies, especially on data stores, you have to decide upfront what level of data consistency you genuinely need during a crisis. Ask yourself, does this piece of data, like a user ID or a session token, truly need to be globally unique and instantly consistent within 10 milliseconds, even when US East 1 is on fire? Probably not for everything. Can you tolerate regional consistency for a while and then reconcile the data later after the storm passes? Trying to achieve both perfect global uniqueness and immediate consistency across regions has been called the architectural lie you tell yourself until an outage. So, decide what truly needs instant consistency versus what can wait. Don't assume everything needs the highest level. When you put every piece of critical data into one DynamoDB table in US East 1, you're not just taking a risk, you're inviting disaster. Build your system to bend, not break. Let it keep running, even if some data takes a moment to catch up. 2. Decouple configuration from region. This is a huge, very practical one. You absolutely must treat the cloud region itself as a variable in your system, something that can be changed, especially in a crisis. How do you do that? Stop hard-coding regional endpoints like dynamodb.us-east-1.amazonas.com directly into your client code or configuration files. Use dynamic lookups or configuration services that can point you elsewhere. Even more critically, check where you store your secrets and identity tokens. If your critical authentication keys, your OAuth signing keys, whatever, are generated and stored exclusively in a key management system, KMS instance, that only exists in US East 1, then your entire global identity system is completely locked down the moment Northern Virginia hiccups. You can't authenticate users anywhere if the keys are stuck there, so you absolutely have to replicate those critical cryptographic dependencies across regions. Treat keys and core configuration like critical data that needs multi-region resilience. And finally, Rule 3. Practice chaos. This might be the hardest, but most important. High availability isn't some guarantee AWS gives you. It's a probability distribution, something you achieve through design and testing. You mean like chaos engineering? Breaking things on purpose? Exactly. You have to practice failure to find those hidden, hard-coded regional assumptions lurking in your architecture. The recommendation from some analysts following this outage was blunt. Chaos engineer your own manual Monday by simulating the failure of US East 1 once a quarter in your staging or test environments. Just turn it off, simulate it being gone. It sounds terrifying, I know, but that is arguably the only way to be sure you found all those sneaky dependencies on Northern Virginia before the real incident takes your entire production system down. Practice the disaster so it's less disastrous when it happens for real. That's the idea. Find the problems on your terms, not AWS's. These are 3 really solid, actionable rules. Rethink consistency, decouple regions, practice chaos. Stepping back for a moment, this outage was a real wake-up call. One technical failure, even a complicated one, managed to knock out banking systems, government websites, and everyday apps people rely on just to talk or pay for things. It was a sharp reminder of how much trust we've placed in just 2 giants, AWS and Microsoft Azure. This situation brings up a staggering regulatory angle to the interdependence of critical services on these providers. Consider the UK example, where the Treasury Committee raised questions about AWS's regulation. Before the outage, the Treasury Committee was already questioning why AWS wasn't formally regulated as critical third-party infrastructure for the financial sector. Then, this happens. ATMs and mobile banking apps stuttering because of a regional failure thousands of miles away in Virginia. It made their point quite forcefully. The lesson seems unavoidable. We're living inside a technical monoculture. This lack of diversity is a growing concern. The antidote is diversity, more multi-region architectures, maybe even multi-cloud, for things that absolutely cannot fail, things touching money, safety, civic life. We have to move beyond simply assuming our safety mechanisms, like multi-AZ. Multi-AZ stands for multi-availability zone, will work during the very crisis they were designed for, especially when that crisis hits the control plane itself. Here's the transformation, the shift in mindset from this video. You are no longer just a cloud consumer. You need to think of yourself as a systems risk manager. Remember that key distinction from this outage. Multi-AZ durability within the region mostly held up. It met its promise for many. But the regional control plane failure, that was the unexpected catastrophic point failure that wasn't adequately planned for by many. That's the risk you now need to manage. It's a critical aspect of modern cloud strategy. And looking ahead, the next outage, maybe not identical, but some major failure, is already brewing. It's guaranteed to happen eventually. It's inevitable in complex systems. So your goal can't be to prevent failure entirely. It has to be about designing systems that are strong enough to make failures predictable, expected, and emotionally manageable. The final provocative action for everyone watching today, based on everything we've discussed, go find out, really dig in. Verify your dependencies. How many of your critical application dependencies, especially around identity, key storage, core configuration, and maybe even DNS resolution, are implicitly or explicitly dependent on US East 1? Don't assume. Verify. Start mapping out what actually happens to your services when Northern Virginia suddenly gets switched off in your tests. You need to start designing for that reality now, for the next outage, not just reacting to the last one. Be proactive, not reactive.
So, let's take a moment to look back at what we've uncovered together. We began with that massive AWS outage in US East 1, a single regional failure that sent shockwaves across the internet. It reminded us that the systems we trust most can still stumble, not because of one broken server, but because of the fragile architecture that ties everything together. Then we dug into why it happened, how a simple DNS issue snowballed into a global slowdown, and how the very systems meant to recover from failure actually amplified it. That was the turning point, the moment when resilience turned into risk. From there, we drew 3 key lessons for the future. First, rethink your consistency. Not every piece of data needs to be instantly global. Second, decouple your configuration from any single region. Don't let your entire system depend on one location. And third, practice chaos. Simulate failures before they happen, so the next outage feels routine instead of catastrophic. When we step back, the bigger picture is clear. We're living in a cloud monoculture. The answer isn't panic. It's preparation. The more we understand our dependencies, the more control we take back. So, as you leave today, take that mindset with you. Don't just be a cloud user, be a systems risk manager. Because the real goal isn't to stop failures from happening, it's to make them so well designed and well practiced that they barely make the news next time. Thanks for watching, and let's make the next outage a story of resilience, not regret.
That wraps up today's discussion. Thanks for watching and tuning in. If you're curious to dive deeper into this topic, make sure to visit our website. The link is in the description below. Don't forget to subscribe and click the bell so you never miss an update. See you next time.